Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine taking a sip of water and realizing that some of the complex molecules swirling within that glass traveled billions of years across the galaxy just to get there. This isn't science fiction. It's the emerging field of astrobiology and hydrology, where scientists are finding definitive proof that the essential organic materials, the building blocks of life itself, are not only delivered by comets and asteroids but are detectable right now in terrestrial groundwater. For decades, scientists have debated the source of Earth's water and its initial supply of prebiotic chemistry. While geological processes create much of the planet's chemistry, the essential complex organic molecules, things like amino acids and specific sugars, require a specific, often frigid, environment to form and stabilize. Enter the comets. Comets, often described as dirty snowballs, are frozen relics from the solar system's formation, harboring vast quantities of ice and complex carbon-rich material that hasn't changed much in 4.6 billion years. When missions like Rosetta met Comet 67P, or when samples were analyzed from meteorites, we confirmed they carry an incredible inventory: glycine, alanine, and even non-terrestrial amino acids. These molecules are the raw ingredients needed for DNA and proteins. But how do these pristine, interstellar components move from a fiery atmospheric entry to a pristine aquifer miles beneath the surface? The journey is surprisingly resilient. When a comet fragment or micrometeorite hits Earth, the impact is immense, but if the object is small enough, or if the atmospheric entry is shallow, some organic materials can survive the heating. More often, it's through the continuous, gentle rain of cosmic dust, tens of thousands of tons of material falling every year, that these organics are deposited onto the planet's surface. Once deposited, these molecules enter the hydrological cycle. They dissolve in rainwater or meltwater, percolating through soil and porous rock layers. It's here, in the secluded, stable environment of deep groundwater systems, that the molecules can be protected from microbial consumption and chemical degradation long enough for scientists to find them. The real challenge lies in differentiation. How do you tell a cosmic amino acid from an organic molecule made by a terrestrial bacterium? This is where scientific detective work gets incredibly precise. Scientists rely on two primary signatures: isotopic ratios and chirality. First, isotopic ratios. Life on Earth preferentially uses hydrogen. However, molecules formed in the cold, dense molecular clouds of interstellar space often incorporate heavier isotopes, specifically deuterium, hydrogen with an extra neutron. A significantly high deuterium to hydrogen ratio, the D-H ratio, in a sample of groundwater extracted organic molecules is a neon sign pointing directly to an extraterrestrial origin. Second, chirality. Many organic molecules, including amino acids, exist in two mirror image forms: left-handed, L, and right-handed, D. Terrestrial life, including all organisms on Earth today, exclusively uses L amino acids. However, extraterrestrial samples, like those found in the Murchison meteorite, often show a slight excess of D amino acids, or a near 50-50 mix. Finding a subtle D excess in a groundwater sample containing rare amino acids is a powerful indication that the source is literally out of this world. Researchers analyze groundwater, often retrieved from ancient, isolated aquifers, using highly sensitive techniques like gas chromatography mass spectrometry. They are essentially hunting for these trace cosmic fingerprints, isolating the water, and identifying those telltale D-H ratios and the presence of non-terrestrial isomers. The implications are profound. This research doesn't just confirm that the raw materials for life came from space. It confirms they are still actively entering our biosphere and surviving the journey down to our deepest water resources. It strengthens the theory of panspermia, where life's building blocks are widely distributed throughout the universe. So the next time you pour yourself a glass of water, pause and consider the ancient, cosmic journey those molecules took, potentially carrying the very secret of life's beginning, delivered right to your cup. It's a remarkable connection between the vastness of space and the vital resource flowing beneath our feet. For more incredible facts like this, don't forget to subscribe and turn on notifications.